All right. Welcome back, everybody. Happy Halloween. I may or may not have robots running up and down the street around my house tonight. The kids have no idea what's coming. Okay, let me just start with a little admin. So I released the feedback. I tried to give comments to everybody. I mean, I read a lot of pre-proposals in a short amount of time, but some of you are mostly good to go. Some of you, said, Drake can't do that. I had to say that a few times, or some of you, I gave some feedback, tried to give some corrections. So please read that feedback and address it. And the goal is to lock in your proposals on Friday. So changing now, fine. Talk to the staff. The goal was to force a conversation to happen through that pre-proposal, but the other goal is to kind of lock things in by this Friday because we don't have a lot of time for the projects, and you want to hit the ground running and not change course too much after that. Okay, so please interact with us this week if you have questions about the feedback or if you want to discuss anything that came up. I guess there's also maybe a little bit to say, and I'll post something on Piazza about this, but I think you should, as you get started on your actual projects, you'll realize, everybody sort of realizes it as they're doing their problem sets, but creating something from scratch is different than filling in the gaps in a notebook. And sometimes it feels like we push you off the cliff, and you have to start figuring things out. So ask questions. We're going to try to expect to be interactive. We're going to have one of the TAs assigned to every project so that you have a tight loop with somebody specific. But I'm also happy to answer questions. I'm happy to, implement things that need to be implemented to help people on their projects and things like that. So please iterate. There's a couple ways you could ask questions. Of course, you can ask on Piazza and the like. But if you're willing, I actually love it when people ask on Stack Overflow, because then I don't have to answer it again next year, So, and it builds up a corpus of sort of answers and things like that. And you can build your reputation on Stack Overflow. So consider that if you're willing. No pressure if you don't want to do that. I do think that there's an art in asking a good question. If you're stuck on something in software, coming up with a very minimal reproduction that I could run or that the staff can run and see what you're seeing. There's a couple tips that I will post just on how to ask a good question. There's some advice from Stack Overflow and other places that is pretty useful. And the people who ask the questions effectively get quick answers. So, any high-level questions about that? Okay, ask on Stack Overflow if you have them. Last time we talked about force control, right? And today I want to lift it to manipulator control. For those of you that have taken under actuated, right, that's about control as a whole, that's controlling the robot and the environment, for instance. Today is about controlling the robot, really. Just forget about the environment. Let's just think about how do we control the robot extremely well, okay? So last time, force control. And the point that I tried to make right before last lecture, we had always sent commands to the robot in the form of desired positions, right? And the point I really tried to make was that some tasks are more naturally or more robustly specified using the languages of force, using the language of force. Or with stiffness or some generalization of that, right? So the examples I started with, for instance, if you have to push a book via contact coming from above, then you need, for this to work, to be pushing down on the book hard enough to have friction between your fingers and the book, but also not so hard that the book can be in sliding between the book and the table, right? So there's a sweet spot. And if you just went through a position control mode and you can't think directly about how hard you're pushing, then it might be very hard to find that sweet spot and effectively move the book around. Of course, you could say, I'll just set my position command lower and lower until I achieve a certain force, and that's true. There's an equivalence there. But that's assuming you know something about the gains that are being used and how they manifest themselves in the end effector coordinates, and it's much more natural to just express the thing in the language of force at the end effector. Okay, we also talked about a similar kind of motivation was if you're trying to stay inside the friction cone and rotate the box up. I made a slightly more subtle point, I hope, effectively, with that example where the box was in the corner, right? Where we talked about programming the interactions directly, right? The stiffness. Stiffness, damping, impedance. Trying to make your robot look like a spring when it interacts with the ground. And the point is that not only can you write things more naturally, but it can really make a huge difference. So the example here of this box where we had a finger here and we set a virtual point here and tried to act like a spring that had a virtual point here. Now, I wrote a very simple controller that just kind of went like this and then went like this. And something very complicated popped out, which is the box started in stiction here. All of a sudden, at some point, it slipped, and it moved very quickly down to here. My command was simple and slow and smooth, right? But the response of the low-level controller was fast and did exactly what it needed to do to snap this thing and push it down, because I'd set a center of compliance somewhere in the middle here, and that was exactly the natural specification, right? I made a quick comment last time, and a few of you asked me about it, about even if you're doing learning control, you might choose to use these kind of representations in the output. And just to make the simplest observation there, but let's say I've got a controller that's like a 100 billion parameter transformer, and it only runs at a few hertz, right? But this interaction is extremely fast. So the command coming out of the high-level controller could be slow and simple, but the resulting behavior is still beautiful and good. Okay, just a bandwidth argument is already enough to motivate that. Okay. The other thing we did last time was we assumed everything was a point finger. We said the robot is just a point, and it had like a fictitious jetpack moving it around, and that made all of the equations easy. And the goal now is to fill in the details and put the robot back and make those fictitious forces come actually from the joint torques. Okay, so last time. Just to remind you, that point finger model was intentionally chosen to be very simple, but it looked like this, right? So we just had the accelerations, which could be the x and the z position in a vector, right? Q was, for instance, the x and the z positions of my finger, okay? And there was a gravity force. Tau g in that case was 0 and negative mg, right? And then there was kind of this fictitious jetpack sort of, this is my actuator. I'll say it was like a jetpack actuator, which one could not build, but it was a good mathematical model. And then we also had any external forces that were applied to the point finger, okay? And so when you see this, I hope you just see, mass times acceleration equals the sum of the forces, right? So F equals ma. All right, so now we want to fill in the details of how do we do that with a real robot. And I hope by the end you'll understand sort of the a pretty reasonable kind of zoo of controllers, right? So there's PD control or PID control. There's inverse dynamics control. There's force control, which you can do in Cartesian or spatial more generally. If you have translation and velocity, then it would be a spatial force. Okay. Then we talked about stiffness control, and you can do that in joint space or in spatial, Cartesian space or Cartesian translation plus rotation. That would be a spatial stiffness. Okay. This is like a library of controllers that you could choose from, and you might choose differently depending on your application, depending on how well you understand the dynamics of your robot. Some of them assume more or less about what you know about the robot. Okay? And it's really very simple. I think the differences there are actually small, but it can be overwhelming, and sometimes it's presented in complicated ways. So I'm hoping that I'll make it simple and clear, and you'll understand by the end of the day. Okay? So just to say that in the point finger case, we sort of understood it already. So PD control was simple, right? So we just said that U equals some position gain times Q desired minus Q plus some derivative gain, Q desired minus Q dot. That was the PD controller that we know and love. If we have the stiffness control, this is also has a damping term. Sometimes people call it damping control, but mostly it's just called stiffness control. Okay. Then it turns out it's almost the same, right? Remember, the only thing that changed was I had the PD terms, but I also took in minus tau g. I also did gravity compensation. And the reason to do that is if you can see that here just subtracts out this tau g. We're going to see exactly the impact of subtracting that out. But what we already showed last time was that the implication is that this is like programming the stiffness of the system so that the closed loop response, I subtract it like this to write it in sort of spring form. I should even maybe, when we write springs, we often write the derivative first. So the interpretation is that now I have a closed loop dynamics that actually looks like a spring mass damper system. Okay, and if somebody does come up and push it, or if I run into something, then the response that my system is going to give is equivalent to what a spring would give if it ran into something. You're right. I switched halfway through and didn't fix it. Yeah. Now, when you're a point robot and your coordinates are the position of that point, then there is no difference between joint stiffness or spatial stiffness. They're the same thing. Okay, which is the nice. But in the full robot case, we'll have a choice of whether we write this stiffness to happen in the sort of in a Cartesian frame or in the joint frame. Okay, we talked about force control, which would be more generally spatial force control. I motivated it with assuming that Q double dot was equal to 0, because then you see that U if you choose just that controller, so you do the gravity compensation and you push in the desired force, then the result would be that my external force equals my desired force. Yep. So in order to move this to the other side of the equation, I needed to subtract. So I could have written minus and kept it in this order. And maybe that would have been, I was debating with myself which one would be clearer. The reason I went and flipped it is because oftentimes if people write spring mass damper systems, they will write it in that order and think of this as the rest length of the spring. So in my mind, it's a little bit more pattern matched like this, but it was just subtracting it by moving it to the other side. Thank you for asking. Mm-hmm. Okay, so we actually already understand most of these, right? The stiffness control, spatial stiffness control, like I said, were the same. The spatial force, we understood in the simple case where spatial is just two axes here. We already understood the PID control. We didn't actually cover the inverse dynamics control, okay? And it should, of course, have a simple interpretation even for the point finger. So let's just finish that, finish the zoo, and then we'll add the robot in, okay? And the reason and the motivation for the inverse dynamics control I think is best seen if you think about tracking. Okay, so let's think about trajectory tracking. Okay, so for a moment now, a lot of times in the derivations, I'll set one of the terms to 0 just to keep things simple, and then we'll put it back in at the end here, okay? Let's assume for a moment that there's no external forces, and I just want to move my robot around. I have a desired trajectory, and I'd like to track it as well as possible, okay? And I'll do it first in the point finger case, and then we'll see it extends nicely to the general case. Okay, so let's think about even two cases. If I say the desired Q is just a constant, that would be sort of my steady state response. And then maybe more interesting, but not that complicated here, would be if I chose some trajectory. I just, for the purposes of plotting, I chose that trajectory, okay? In both x and z, I just asked it to follow a sine wave. I should really... a vector. Okay, so what do the different controllers do for this? So PD control, in the case of it being a constant desired trajectory here, I have like time Q desired here. Maybe it's just the z-axis, for instance. So this is my, let me call it z here, and then this is Q desired. So what is my robot position going to be if I'm using PD control? Yeah. Right. Exactly. That's the intuition. It could start somewhere, it might have a nice response, but then it's going to end up being lower than the actual one because it doesn't take into account gravity. And if you need sort of a simple way to think about that, if you take the equations of the finger under PD control and ask what happens if Q is exactly at Q desired, then this term is 0. And if my velocity is exactly at the desired velocity of 0, this term is 0. That would be the ideal case. Would be I'm at the location. My feedback control is kicking out 0. Okay, I put in a 0 here. This is 0. I still have an acceleration pulling me down. So I'm not at a steady state. If you put it exactly at the desired location, it's still falling with gravity. And it's not until the gravity term catches up to the feedback term that they find a balance, and it'll end up being a little bit lower. And similarly, when you put this in a trajectory loop, then you'll see that it will have a persistent error. So now if I have the blue is my desired trajectory plotted in Z, okay, then you'll see a persistent error from a PD controller. Okay, it's always tracking. It's an error-driven controller. It's always tracking where it was, you know, and it will never restore gravity, and it'll never quite catch up in some sense. Okay. The stiffness controller subtracts gravity out, so you should expect that to do a bit better, right? In the PD, or in the simple case, we could expect the stiffness controller to come up and converge nicely. It does. It could have 0 steady state error. If I put Q desired in as my Q, this term is 0, but I still get the gravity cancellation, the acceleration is 0, and it will stay at the fixed point. Okay, so it does better, but it will still have a persistent error. Right? Yes? You could think of it as being because of the lag of the controller. Right? But you could also just think of it in the equations. If I say that if I have this as my desired and I have Q dot desired T, then what is MQ double dot? I've got tau G minus tau G. So that part gets canceled perfectly. Okay. And then I have KP QD minus Q. If I'm exactly on my trajectory, and these terms are also 0, then that's great. Q double dot will be 0. Okay, but Q double dot desired is not 0. Right, so this does not equal M Q double dot desired. Okay, so instantaneously, it's not tracking the trajectory. Makes sense. There's something else we knew that we didn't tell our controller about, which is that the trajectory is changing. It's not, you know, it's got acceleration. So the natural extra thing, and the extra term that you want to add in, that is exactly what the inverse dynamics controller adds in, is a feed-forward acceleration. If you tell your controller there's also acceleration, you can do better. Yeah. Good. So let me write down what the inverse dynamics controller is, and then we'll ask, is it too noisy to execute? That's a good thing to check me on. Okay. So the motivation, see, for inverse dynamics controller isn't present in the steady state response, but it is present if you have a trajectory. Okay? In subtle ways, in the manipulator case, you could still even see it there, but so the goal is to add that in. And the natural thing, the way to do it would be to choose, I still have my gravity compensation, and I'm going to add in MQ double dot desired. In practice, so now that we're bringing M in and we are assuming that we know M, we actually also multiply the PD gains by M. Which looks like an arbitrary scaling when it's a point finger. It's just a scalar M. I could have just multiplied KP. Okay, but when M is a function of position, then this can be nice to shape. It's easier to set PD gains in the acceleration coordinates than in the torque coordinates. Okay, I'll make that point again when we write it. Okay, but you see, this is the stiffness controller with basically one extra term, and it gives us the best tracking that we have so far. basically as well as you'll expect to do. And in particular, the thing that you can see about this is that if you write the closed loop dynamics, then actually the best way to write it is to not write Q double dot. It's to write, let me define Q error as the difference between the desired and the actual, right? And I can similarly write the error derivative and even the error second derivative. And the beautiful thing is that if you run this controller, then the closed loop performance these are all errors, so I can write this. Let me write it in the error coordinates. Okay, now the error dynamics looks like a mass spring damper and will converge nicely to 0 as long as you pick Kp and Kd to be a stable spring mass damper system. Yeah?
Where does the second derivative of Q desired? Or is that like supposed to be the right hand side? Like, what is this?
So I have to write a controller. I'm going to take, it's going to produce torques. I'm going to stick it into the, by executing the torque on the robot, I'm effectively sticking it into the physics equations, right? So I end up with a mq double dot desired that comes in here, which I move it over here, and it looks like mq double dot tilde, mq tilde double dot.
So in this case, the controller knows, like, has some estimation of the future desired? Because they have like a second order derivative.
Yep. So if you know, if you're, so yeah, if you know that you're going to execute a trajectory and it's parameterized nicely and you have that available, then you can do better by telling the controller about it. There's some cases where you don't know what Q double dot desired is going to be, right? But if you just want to paint a picture or something like this, then you know what that is and you can track it better by passing that to the controller. Yes?
Are those controllers perfectly tuned? So if they are blind, or like way that is not called.
I could make the response arbitrarily fast. I picked a Kp and Kd to have a response that made it visible on the plot. Yeah, but for sure I could. But you pay a price by turning the stiffness up, right? But you could get faster convergence. Yeah.
The inverse dynamics control are very good. So I would just assume maybe because the double dot came very quickly.
Mm-hmm.
So if it would not be, I guess if we not continue at all, like jumps in the second order, or like just curious, when would I choose this inverse dynamics controller?
Thank you. That's that's kind of the goal. So if you know Q double dot and it's smooth, if Q is C2 continuous, then I would typically say you could do better, with one extra caveat, which is that it does assume you know your mass matrix. So in the cases where you don't know your mass matrix well, then you could actually potentially do worse by pushing that through. Yeah. Even in the case, by the way, when we have an external force, right? That external force is going to appear here too, shaped by the mass matrix. Okay, but it's like 1 over m roughly times the external force here. But it's still going to have a good response, even in the presence of unexpected forces. Okay, so I mean, given these equations, it's sort of, I think the progression is extremely natural, right? You're just going to, oh, I can cancel out that term. Oh, wait, I can cancel out that term. And you're just adding a few more things. And this gives us a whole library of possible controllers. They assume a little bit more. All right, so when you get to this sort of wall of different control approaches, I hope you think back and just realize it's just adding one or two more terms to do the cancellation. They get a little bit more hidden when I do it in the manipulator equations, but it's exactly the same. Okay, so let's do that now. I've written the manipulator equations a few times. We're going to use them a lot here. Okay, so we're just going to write the generalized version of that. Okay, the generalized version. In the case of robot control, where I know I don't have any floating base joints or anything like this, I can just use Q double dot and be safe about it. I made a point earlier that don't assume that the velocity has even the same number of dimensions as the positions. So I would typically write v and v dot. But for a robot, for control, Q dot does equal v. We don't have any quaternions in the middle of our robot that we're trying to control. Most of the time, almost always, right, in the robot manipulator case. Okay. Right. It's almost exactly the same as that. This is just the generalization of MA. Okay, it has the inertial matrix. These are the Coriolis terms. But really, you should think about those things. Those things come together, right? The Coriolis terms and if you change coordinates, it will shuffle MA. This is just the leakage of the core of the acceleration into some extra terms. Okay, so those go together. This is not like a Coriolis force, really. This is really the acceleration just manifested in that way. This is the gravity torque. This is now has an explicit understanding as the joint torques. Right? But it's otherwise almost exactly the same. And we know loads about these equations. Like they're very structured equations. If you run these through you generate them for lots of different robots, you'll see that there's patterns that emerge. There's efficient algorithms for computing them, by the way. There's like nice recursive algorithms that can run up and down the kinematic chain to compute them very efficiently. There's properties like one that we'll need here is that the mass matrix for all Q is positive semi-definite. Okay, so we're going to be able to, if you squint a little bit, for these robots, it's always going to be strictly positive definite, and we're going to take mass matrix inverse. That's going to be okay, right? And there's other properties that you can exploit if you get into the world of control. I saw a hand go up somewhere. Yeah. Yeah. So in the point case, everything's nice and convex. You get some complexity in the Q terms here. There's actually some really cool things you can do. So it turns out if Q is fixed, everything else is convex. So if you have a path, you can do like time parameters, time optimization in a convex way. So many things can be formulated in that way. But in the general case, we need to manipulate the nonlinear equations in order to do gravity compensation. That's a nonlinear thing. And shaping the inertia and stuff like this. These are nonlinear things.
So long as I'm near the correct path, like maybe I'm very naive.
No, no, you're
I
good.
would expect that gravity would be fairly continuous as a function of my robot code.
Yep.
And then so long as I can ensure that I'm near the path, then the gravity is like a second order correction, right? So let's say.
That's a great question. So, yeah, if you were to have a desired path, then like linearizing the equations, making a convex approximation in the vicinity of the trajectory can be a useful thing to do. And we actually, in more complicated systems where we don't have closed form controllers, we fall back to doing that. Okay? In this case, we don't need to do that because the equations are so structured and I have enough control authority that I can just take exactly the right non-convex corrective terms. But your statement is true. Yes, absolutely in the vicinity you can do well with local convex approximations. Yeah. Yeah. Yep. No, I think so. In almost every case we will ever see, it's going to be positive, strictly positive, definite, right? The things that you have to watch out for are, for instance, like I did it in the mobile manipulation lecture, I added massless actuators to be massless bodies between actuators in initial joints. I still think that is probably positive definite, but that's the case I would want to check for. You could also, like the broad class of kinematic trees could involve massless elements on the leaf, but you don't ever want to put those in. I think in practice we always treat this as a strict positive definite. I think for every reasonable system we would expect that to be true. So maybe I think the thing that Cheyenne's saying that he knows that maybe some of you know is that you can write the kinetic energy of this system that's the kinetic energy, right? So, and kinetic energy, is going to always be positive if things are moving. Okay, so that's maybe one way to have intuition about, if m was 0, that's a little weird that you could say you could move without having kinetic energy. Yeah. So I think for all intents and purposes, I'll see if I can come up with any practical example where it's has a 0, 1, 0 eigenvalue or something, but right. Exactly. Yeah. I think there might be cases like that. So he says with degeneracy, maybe if you have kinematic chains or something like this. It's fair. For today, it's invertible. We're good. Okay, so now that we know the simple recipe of like PD control is this, right? Then it turns out that joint PD control is exactly the same as that. I take and use exactly that same PD controller, and I've now got it in a joint space, then this pops right in, and I have a joint PD controller. Okay, I was planning to write it all, but I think I might have been effective enough with my choice of board locations that I could just point. Okay. So there's nothing changes in our PD controller. It's just that the interpretation is now not just X and Y and Z position, but it's the joint positions. And I have a proportional and derivative gain in the joint positions and their derivatives. Okay, so that would be joint PD control. Joint space PD control. If you do joint space stiffness control, then you'll add in the gravity compensation term, just like we did before. And that gives us exactly the analogous thing here, right? So now we're going to act like we're programming the stiffness and damping in the joint coordinates. Okay, so we're going to act like if I bump into something, the response I'm going to get is as if my joints were linear springs, right? And damped linear springs. So that's super useful, right? And then the inverse dynamics, we're going to, I'll write this one out just to, because it's a slightly more complicated. I'm going to do my gravity compensation, and then I'm going to shape with the mass matrix a feed-forward term plus my PD controller. When I plug that in to the dynamics, what I get is that MQ double dot I get the error dynamics with an M in front of it here. But M is invertible, so convergence in this system implies that Q double dot goes to Q double dot desired. I could write the whole thing out, but this is almost exactly what I wrote for this case here. I have MQ double dot times this whole thing. I'll write it out. KD Q tilde plus KP Q tilde. This thing equals 0. And because this matrix is invertible, for this to be equal to 0, that implies that this thing does indeed, that Q double dot converges to, and Q absolutely converges to Q desired over time. Yes? It definitely matters. You're right. The actual term is going to be subtracting. Thank you. It absolutely matters. I think of it as adding in a gravity comp term, but you're right. The symbols I have gravity comp being like that. Yeah.
Sorry, maybe I'm missing something. Why does M have to be invertible for it to converge?
If M was 0, then this thing could do arbitrary things, and I would still achieve this equation, right? So just by virtue of being able to multiply both sides by M inverse, I can guarantee that this thing itself is 0. Yeah. Yes? Yeah, that's a really good question. So since we're canceling terms, why not also cancel the Coriolis term? Yes, so where did I lose that in this derivation? I guess I didn't include it here. Let me make sure I get my algebra correct, and then I'll answer the philosophical question. I think I forgot to write the Coriolis cancellation here. I would also add in the Coriolis terms here to cancel. Yeah, I should do that to get the full cancellation. Yeah, thank you. Yeah, the goal is to get to here. So you absolutely do cancel that. Mm-hmm. Thank you for catching me on that. took my point mass example too far. Okay, going back to your question from yesterday about gravity comp versus PID, right? So when we first said that there's a steady state error, then a natural response would be that you could also get rid of these steady state errors by doing an integral term. But instead, I'm advocating for doing gravity compensation, right? And the reason for that was twofold. First of all, integral terms are a little dangerous. When you start pushing into something that will push back with arbitrary force, then you'll get a wind-up. You might push arbitrarily hard. Gravity compensation won't do that. Okay? But there's a second thing, too, which is that having that gravity compensation allows me to choose lower gains. I can still get good tracking, but where the PD controller in practice will tend to have a very large KP and KD because you want to be able to follow your trajectory accurately. And part of the reason you have to pick it large is because it's trying to it's trying to make that gap small. It's trying to fight against gravity. Okay? And because gravity moves in different configurations, you tend to ramp up all of your Ps, your KPs and KDs. By simply subtracting out the gravity terms, you can already get a much looser interaction, much more lower stiffness interaction. Yes, you can choose Kp and Kd to be lower, and it's even more true in the inverse dynamics case. Why? Is because you're shaping the response in Kp and Kd is now uniform. It's written in the coordinates of acceleration. It's uniform even if the mass matrix is changing, right? The resulting dynamics are simple in this form, and I can tend to choose low Kp and Kd. I don't have to choose like the largest Kp and Kd for the worst case mass. I'm going to cancel that out. And in practice, there's something sort of subtle that happens. Okay, so the controller that you have implemented on the EWA, it is officially an impedance controller, but from the user's perspective, you don't get to shape any inertias. You should think of it as a stiffness controller, okay? But in simulation, actually, we often model it as an inverse dynamics controller instead of a stiffness controller, even though that adds a little bit of sim to real gap. I can simulate, it's not much, and I can turn my gains lower, and I can take larger time steps in my simulator because my equations aren't as stiff. So actually, if you look in like hardware station, you'll see that I add inverse dynamics controller, not stiffness controller. Because otherwise, if I put the KPs and KDs that you would enter into the stiffness controller on the KUKA hardware, then that makes it so you have to take very small simulation time steps because you end up with a stiff differential equation. And you can get similarly good tracking performance with lower gains when you use inverse dynamics control. Super subtle point, okay? But that's true. And actually, next time I teach the class, I will be using stiffness control again because we made our integrator better. And so I can actually take the same stiffness control and simulate it almost as fast. And I thought about changing that, like it happened a few weeks ago. I was like, I could change everything right underneath and maybe no one will notice, but I just didn't want to. So I'll probably do it at the end of the semester. But because it's kind of a little scary ripping the heart out of everything that you guys have been doing and sticking in a different heart. But probably after the term, I'll clean that up. So better numerical recipes, which take some of the stiffness into the time-stepping integrator, have allowed us to simulate more with the more accurate joint stiffness controller at high rates. Okay, so yeah, the goal here, if you're thinking about joint PD control, joint stiffness control, joint inverse dynamics control, is really about allowing the robot to be more softer. It can execute your desired motion plans, but when things go wrong, it has a softer response, right? And that is like super important, right? So this is my favorite example of it is that if you watch when we open the dishwasher door, or when you guys open the door of the cupboard, right? You're in your problem set, right? You're in a compliant mode. You have fairly low gains. So if your trajectory that you planned was a little bit wrong, your estimate of the door kinematics was a little bit wrong, like if you were in a stiff PD control mode, then you would potentially create very large forces as you're fighting against the kinematics of the door. Rip the door right off, maybe, right? Depending on how strong the robot is. If you're soft, right, then you just, when you're in free space, you get extra accurate tracking, which is important because otherwise you'll miss the door. You'll plan carefully, you'll reach out, you want your fingers to get in between the door handles, right? But then once you grab it, you need to be flexible enough to fit the kinematic constraints and execute that opening. And without that, if you were with a stiffer robot, then you would not be able to do that. Okay? So the fact that the low-level KUKA controller implements joint stiffness for us is partly due to their ability to have torque sensing and things like this, right? So it's not all robots can do that. But when you have it, you can be a lot more gentle in the world. Yeah? Does that kind of make sense? Cancel out more terms, you get to be softer. Basically, that's it. Okay? So this was all in joint space. In our zoo of controllers, right? That was, so we understand pretty well PID control, inverse dynamics control, joint stiffness control, but we haven't yet talked about the spatial versions of these controllers. Okay, so now I have a complicated robot with lots of joints, but I want it to act like a simple spring mass damper at the end effector. Okay, that's the last beautiful step. Maybe I'll even show you what it looks like first, okay? So if you look at the sort of KUKA promotional videos here, what would it look like if you were to program yourself to act like a spring at a certain point, right? So at the end of at this end effector, you get to set a stiffness, right? And he's now set a softer stiffness, right? You push on this. You might think if you're working directly in joint space, you push on it, it might do some weird thing, right? But it's acting exactly like a spring in the translational component of the end effector coordinates, right? Now he's going to do difference, so it's stiff in this dimension, okay, but soft in this dimension. And this dimension is also soft. That dimension is really soft, but the original one, right? So that's programmable stiffness, super useful. Okay, you want to be like, if you want to follow a line on the to draw something on the board, okay, but you don't know exactly where the board is, you can be soft in the direction you don't know, okay, but stiff in your line following, for instance, in the other axes. And it's cool to do it in, this would be the other half of it, which would be the rotational components. So if you act like a stiffness in the rotational frame, so that one, I didn't point to it carefully enough. He said his translational stiffness was very low, but his rotational stiffness was very high. Okay, now we're going to say translation is stiff, rotational is soft. Yeah? Translate my German there. Or just find the English, actually, is what happened. Okay, yeah. That's the intuition. Okay, how do we make it work? It turns out, and this is a really clever thing, okay? It turns out that we have the dynamics of the robot, and we wanted to cancel them out, and it was natural to cancel them out. We have the dynamics naturally live in the joint coordinates, and we're going to add the extra terms in to cancel out dynamics. So the really clever thing that happens is we can write the dynamics of the robot in the end effector coordinates, which just sounds weird. I've got 7 degrees of freedom here. I'm going to write it just in the end effector coordinates. And of course, it's going to be some projection onto the end effector coordinates, and there's going to be some null space of that projection, and we're going to be able to use that, okay? But let's think about writing the robot dynamics in the frame of the end effector. Okay, and it goes like this, right? So the key idea here is program the stiffness, or more generally the interaction, at a point. Okay, so let me call it, I'll call that point the end effector, position of the end effector, right? And I'd like to think about forces, for instance, that are being applied to the robot body at that point. So this would be my external force. Applied to robot body B at point E, at position E. Now here's a big one if you haven't seen it, right? My equations of motion had this tau external, right? So if I have a force being applied at some point on my robot, then how does that map to the torque external? Okay, it turns out that tau external is the Jacobian of that end effector, okay, times the force external. It's like one of the most important fundamental sort of equations in our robot dynamics. If you want to map between force and torques, you go through the Jacobian transpose. Yes? Good call. Yeah, so this is specifically thinking about programming the interaction there. The behavior would be less beautiful if you pushed somewhere else on the body, right? And that's a point I'll try to make at the end here. But so if you know where you're going to be interacting with the robot's going to be interacting with the world, then you should be using, you know, this kind of machinery and programming it at a point. If you don't know, it's actually maybe more natural to program in joint stiffness or joint impedance, because the reaction is really focused at a point in this case. It's a really good point. Yeah. Pseudo inverse or something. It's a transpose. Yeah, I could show you why, right? So this is from the principle of virtual work. It's a variational principle. D'Alembert. It's like 3 lines, so I can. It's not a big distraction to do it. Let's see. So, what work is force times displacement. And the idea in the variational principle is that moving in the Cartesian world, the work you do at the end effector must be the same as the work you do from a variation in the joints. Okay, so if you do that, then you get, in the end effector coordinates, it looks like this, FBE. It's something like this, where this is a variation in position. It's like my incremental distance. That's a dot product, so that would be equivalent to FBE transpose delta PE. But it has to also be equal to the torque equivalent, which is going to be JQ times delta Q. Sorry, this is a torque times delta Q. I jumped a step. Torque times delta Q. Transpose times delta Q. But delta Q and delta P are related by the Jacobian. So delta PE is the Jacobian times delta Q. So if you set those equal, then it really is delta PE gets the Jacobian, but I take the transpose around, it really does come out to be Jacobian transpose. It's not a pseudo inverse or anything like this. It really is. Just says the work has to be the same. This is sort of the fundamental. This is the way you derive Lagrangian mechanics and stuff too, right? So the fact that you can ignore internal constraints, internal forces, using the principles of virtual work. Big idea. Okay, so this is our mapping, and people use it all the time. Like if you're trying to command forces at the end effector of a walking robot at the foot, you're going to be applying torques using the Jacobian transpose. This comes up all the time. Okay. All right, so let's now write the dynamics in that coordinate. Maybe I'll do it on the next board so that I can leave both of those. So I know that the end effector is related to the joint angles, with my forward kinematics. It's unfortunate this is also the same symbol. This is my forward kin. Right? It's not a force. In the LaTeX, they're separate. They're distinct. On the board, my font is not rich enough. That's satisfying. In the spatial notation, the spatial accelerations, we use A for the translational accelerations. All of these things have corresponding, almost identical things in the rotations. This one's a little funny. We haven't done it before here, but you can just use the chain rule to take the derivative again of this, the time derivative of this again. So you get, derivative of this times the first times the derivative of this and the second. J dot Q is a well-defined quantity. Okay. Typically, you would only every time you ever see J dot, you'll also see Q dot. This is a term collectively that you can ask Drake and other software engines for. Okay, it's a common thing that pops up a lot. So this is the acceleration in terms of my joint accelerations. I can solve for my joint accelerations for my multi-body equations, right? That's MQ inverse of the rest of it, tau G Q plus U minus C Q dot U dot. So I can stick that in here, stick this side right in here. And I can write P double dot. Given my knowledge of my current configuration, I can solve for what P double dot is, the dynamics of P double dot, or the dynamics of P. Okay, and you can end up with a set of equations that looks a lot like the original equations. It still has Q entering in important ways. In particular, in the Coriolis terms, they don't disappear as nicely as you might think, but okay, so this is my gravity terms mapped into the force at the location. Okay, this is my actuator command mapped through the Jacobian transpose into the end effector coordinates. This is the actual end effector disturbances. And similarly, this is my end effector effective inertia, mass matrix inertia of the system. Yes?
So I have one question about the P dot part equals to V, because the end effector is a point, and the derivative expression is not necessarily exactly as spatial velocity.
So this is my translational velocity. Yeah. So I only mean so I'm thinking of this as a 3-element vector position. This is my, yep. if you remember, I used capital V for spatial, lowercase v. The notation is something like this, yeah? Yes?
What is F
F
sub u?
sub u is knowing this, I normally command u, okay? But I can say, I wrote it down carefully somewhere here. If I have so think of fu be as my command, my actuator command in end effector. And I can achieve it by commanding so the mapping of if you want to command like you had that jetpack force at the finger, then the Jacobian tells you what torques you needed to apply to produce that jetpack at the finger. Yeah, that's basically the jetpack. So the exact terms for this are a little bit ungainly, and they're in the notes. I wrote them out carefully, okay, but these all have a similar form. Sorry, yeah. That's a big question, and that'll depend on your application. A lot of times, the goal of control is to say that, so in most of these derivations, we assume it's not known, and we say that that we want to have a good response, like acting like a spring, something stable response, and you make very minimal assumptions about this, like for instance that it's passive, that it won't actively add energy to the system, okay, that the total interactions are passive. Okay, but typically we treat this as just a disturbance. If you can measure it, the same way if you know Q double dot, you can do better by canceling it out, right? If you do have measurements, then you can do better. You can turn down your gains more and stuff like this if you can measure that, okay? But in these derivations, we're mostly thinking of this as an external unknown disturbance. And I want to make sure that it enters the equations in a benign way. Lots of symbols. And I won't do more of them because these expand out and they're in the notes, okay? But the essential point is that the dynamics of the system written in the end effector coordinates looks a heck of a lot like the dynamics of the original system in the full multi-body coordinates. And we can do exactly the same control approaches. We can do a stiffness control. We can do PD control in the end effector. We can do, by just setting FU, BE to a stiffness to PD commands, then we've got an end effector PD controller. If we cancel out the gravity terms, we have an end effector stiffness controller. If we take out the acceleration, we can do sort of dynamics, we can take the inverse dynamics equivalent in the end effector coordinates. Right? Now that's beautiful. That gives you what you saw there, right? You have your whole robot. It has mass distributed, it has complicated kinematics. You push on it and it feels like you're pushing on a spring. Right? Just by shaping these equations. Right? Now the linearization, the convex form of this wouldn't give you that. Right? This is actually just reshaping in a nonlinear, non-convex way, writing it in a different coordinate system and getting a beautiful outcome. Okay? Now, unlike the joint versions of this, there's something left here because if I only did translational coordinates, if I only tried to shape 3 translational coordinates and I had 7 actuators to do it, then I've still got a null space. So the same way I did in the differential kinematics, and I did something in the null space, I put a secondary command, like for instance centering. You can put secondary commands. You can have a whole prioritized set of commands that are doing multiple objectives in end effector coordinates or other various points. Typically, you'll have one that's living in the null space that's doing a joint centering kind of behavior, keep you nice, okay? But you might actually, if you want to program more complicated things like, I want to push here and I want to push here and I want to go like this, then I can write a prioritized control saying the most important thing is my center of mass stays inside, okay? And I can act like a spring at my foot and I can act like this, and the null space projections put them together. The null space projections in the kinematics case was in the velocity null space. In this case, you have to do the acceleration null space. They call it the dynamically consistent null space. Okay? But it's the idea is the same, right? And that library of different things that you might compose is the famous operation space control approach. Yeah, so this is put together, this is operation space control. Let's see, people call it OSC, for instance. Okay, so for a KUKA, you tend to only have like maybe one extra, a joint centering objective or something like this. You probably don't have a whole library, but if you're a humanoid, then you can things get a lot richer. Any questions about that? Yeah. Yes. Yep. So let's even take the case. Well, I guess I have probably almost have both of them on the board at the same time, maybe. If I had I'll just take this one. Okay. Let's say I have a joint centering kind of controller that's just, let's say Q desired is just my comfortable position. That's going to propose some U, right? I could do the stiffness version of it. I could do just the PD version of it, right? But somehow that's going to give me a U in the full coordinates. If I just took this controller, the U that was commanded from this controller, and the U that was commanded from this controller, they would interfere. So all I'm going to do is I'm going to take the U from this controller, the joint space controller, and I'm going to put it through a projection that projects it into the null space of that controller. So it's allowed to do as much as it can against this objective, but only if it doesn't interfere with the primary objective. Right? So you can actually mix and match spaces as long as you leave the other one to be not interfering with the primary. And you can make a whole hierarchy of those. The joint space will be full rank, so it won't have a null space. But if you had two hands, then you maybe have extra degrees of freedom left for something else. Yeah. Yeah. So same as in differential IK, if you don't specify completely if you have an end effector only objective and you have extra degrees of freedom, then if you don't regulate it, depending on how your pseudo inverse is solving, it's going to pick something for you. It could potentially walk around, and you might not be happy with that. You might have motion. So don't leave it to chance. Give yourself at least the lowest priority, something that's sort of a joint centering or something that's guaranteed to be full rank. Yeah. But if you did leave it to chance, then you would accomplish the original objective, but you might be wobbly in the other objectives, for instance. Okay, I just have a few minutes left, so let me the core concept here is that I can make my big complicated robot, no matter, it could be a humanoid, it could be a KUKA, and I can make it act like something simple. And so you remember my initial box flipping example, right? I can program that through my whole KUKA and have the interactions be exactly what I want. And I think my favorite example of that is actually people have taken that to the point where they realize not only could I program a virtual stiffness in the world and get robustness out, people figured out even a long time ago, this is like in 1977, I love that it's the guy's name is Drake, I just thought that was cool. But so they said, okay, if you could program that, that's great, but I could actually build that in hardware, okay? So Drake and others, decided to try to see if they could make a physical interpretation of this sort of virtual compliance, where you basically want to put the compliance of your robot not at the point of interaction. You want to make it as if there's a virtual spring in front of your interaction. They call it a remote-centered compliance, okay? So here's the idea. So a lot of people back in the 70s and early 80s were thinking about peg and hold type insertion tasks. That was the sort of canonical industrial need, was to try to do force control in order to get peg insertion. If you get that wrong, you can get jamming effects. So if you have a stiff robot shoving a peg into a hole and you get a little misaligned, then you can just like jam the whole assembly. Right? It'll just get stuck, like really wedged stuck, okay? So they think about programming the force and moment, the stiffness, kind of at the end effector. But to make it stable and robust to uncertainty, you can actually push it beyond the end effector, or you want the force and rotation to be at the end of the tool, of the tip of the insertion, not at your end effector. So we now have the machinery to program robot torques to do that. Okay, but just a really cool observation. People built these awesome assemblies. You can still buy them today. They're still super useful, okay? This is like a bunch of leaf springs and other complexities, okay? But they're designed to make a system of springs so that it had a remote center of compliance at the end effect, beyond the hand, down at the tool, okay? It puts this instantaneous center of the beam deflections way down here, okay? And what happens then is when you're coming in, if you have uncertainty, the system just passively falls in to the hole just because of mechanical compliance. And so this is like, old videos, and actually this is much newer than the work that was done. They have these assemblies that look like this, complicated springs that put the center of compliance low. And then they have things that with a stiff robot, a tight insertion task, and they just go wham, wham, and they're like, it'll zoom in a second here. Okay, there's like peg and hole happening here, and they're just like mating these objects at very high speeds and letting the remote compliance make the system that would be traditionally passively very unstable become passively stable just by programming the interaction like that. I love that example, especially since it was Drake. That was total chance. I had no idea. Cool. Okay. See you next time.